explain how the lights work.
Welcome. I'm Erin Moore, and I'm representing the Architecture Department Lecture Committee this evening. So in that capacity, I have a couple items of business. One, if you didn't already give me your AIA number if you want to get credit for attending, you can find me after the lecture. And second, our upcoming lecture is Sarah Architects, Walker Templeton, who is an MArch 2005 grad, who's on the project team for the EMU project, is scheduled for a week from today, Monday, which unfortunately is Martin Luther King Day, so we are moving that lecture 1 week into the future, the 27th. So you'll hear this updated by email, but I wanted to make sure that you have that on your radar, to make sure that you don't miss that. So the other thing is to make sure that we credit the Walker Warner Architects for sponsoring this lecture. We're very happy to have their support, and this is the inaugural Walker Warner lecture. And in that capacity, I'm really pleased to be welcoming Tine Hegli from Snøhetta. Tine is a senior architect at the internationally renowned architectural practice. I don't have to tell you internationally renowned architecture practice, Snøhetta. Snøhetta is named from one of the highest peaks in Norway, and I was curious to find that that peak is 7,500 feet tall, which, if you want comparison, would be comparable to our Cascade Range, sort of the craggier ones like Mount Washington or Diamond Peak. You can make a connection. So the Snøhetta, the firm, received the Aga Khan Award for Architecture, the Mies van der Rohe Award for Architecture. They are doing projects now in Europe, Asia, the United States, and Canada, from offices in New York City and Oslo with about 130 staff members now. So among other prestigious projects, Tine Hegli has taken part in the process and production of the Oslo Opera House, the National September 11th Memorial and Museum, Ground Zero, and the King Abdulaziz Center for Knowledge and Culture in Saudi Arabia. Since 2011, she's been assigned as a process leader in the development of the Powerhouse project. This is energy-positive commercial buildings, pioneering work, supported by the Research Center on Zero Emission Buildings, ZEB, run by the Norwegian University of Science and Technology. She's also involved in the ZEB pilot for an energy-positive net zero emission housing project, which is interesting in thinking about new parameters for the impact on domestic architecture. So we're very thrilled to be able to honor this intersection of high design and leading-edge building science, and also to hear about it from Tine in person. So please join me in thanking Walker Warner Architects for making the lecture possible, and also in welcoming Tine Hegli to the University of Oregon.
Well, thank you. And thank you for inviting me. I just had to start saying I'm so impressed with all these students showing up 20 minutes ahead of the lecture. I've never seen anything like it. I hope I don't disappoint you, and I hope I can keep you awake since it's quite late and quite dark. I will go through 4 different projects. I'm introduced. I'm the architect. I'm part of a team, which is a Snøhetta team, which I will say a little more about. And I'm also part of a super team, where I've been the process leader, a new role for an architect, where we are an interdisciplinary team-working powerhouse league. I will start with telling you a little more about Snøhetta and how we work. As Erin said, we are named after a mountain. The company's been there since 1989, when they won the Alexandra Library competition, and that took until 2001 to complete. So they had a long and slow start. The company has got 2 different studios, and we actually are starting up a 3rd studio in San Francisco with the SFMOMA extension coming up soon. And as you can see, the 2 studios have a little in common. If you can see on the map, we all started in Oslo. Then the New York studio was opened, and we won the World Trade Center site competition. And they found a suitable site is the 25 Broadway on Manhattan, and I was part of the team that actually transferred this competition, one in Oslo, to New York and started up growing this studio, and now it's actually the same size, Oslo and New York. We like to stick together. The two studios are having a lot in common. We are meeting up every year to actually climb the Snøhetta mountain, just to keep our minds open, to exchange ideas, to lay out strategies, to get really worn out and to have a great party. We call it Dovre conversations to make it sound like it's really like a seminar or something, but it's actually more like a melting pot, a workshop. As Erin said, we're about 130 employees altogether. We do have a few common projects where we swap employees from one studio to the other. It seems that the Oslo employees always would like to go to New York, and the New York employees would really go to Oslo. So it's quite easy to find these common projects where we can share our interests. We also like to feel home in both studios. You can see the kitchens and the work environment are a bit similar looking. It looks like we got more food in the Oslo office, I realize. But actually, the New York office is doing just as many projects and have lots more income at the moment. We have different ways of work, and I think I was just having a tour of your studios a little earlier. And the way we work is everything is teamwork, like you were a student. We actually organized very much like the students are in the university. We are being thrown into different teams all the time. It's a very high degree of transparency. We don't really have a hierarchy. I can work as a project leader, a process leader. I can be doing all the details for the opera, and the next week I can be lecturing somewhere. And most of us are being thrown into this from as soon as you would like to, or even a little earlier, which is actually quite a good environment you can challenge yourself, and we learn to challenge each other. We are prototyping a whole lot. We work analog with models, and we work digital in models, and we do this in parallel. And what I could see from your studio work is a lot what you're doing here as well. We also have a lot of workshop, 3D digital printing. We have a large industrial robot where you can make one-to-one mock-ups. We have a man leading the workshop who can actually create facade mock-ups, which I've mounted outside my office place, so I lost all my daylight for a while there. But in a way, it's just it's part of testing out your ideas as we go to make all these models. The Snøhetta way of work is, I'm trying to create some sort of order into our work. And I think maybe a part of the approach is to be both poetic and pragmatic at the same time. And we tend to be known for our really strong concepts. And the way we work in these teams is from the early sketch, we are creating a common concept on the poetic level, which hopefully is so strong that it can lead us through all the different stages, all the way to construction site, without us losing the beauty or the poetic dimension of the architecture as it's being thrown into the one pragmatic discussion after the other. So for the Oslo Opera House, it's a very good example of how the first sketch model describing a Norwegian landscape of sort of walking on snow and ice, and it actually survived in the same shape all the way from the competition entry and to its completion in 2007. What we were focusing on, and this is sort of sustainability in a sense where the social sustainability is maybe more important, where we think when we throw in this much effort and economy into a culture building which is so sophisticated as an opera house, we should make sure that the public gets as much of the house as the audience of the opera. And this is actually a sort of double the program exercise where we get twice the program out of one opera. We got the opera inside, and then we got the public plaza, which is actually a lot more popular than the opera inside, and a lot more visited also than the opera inside. So every time there is a new visitor coming to our home in Oslo or anybody else's, doesn't matter if they like architecture or not, They will bring their grandmother up to the roof of the opera, pay nothing, and haven't seen the city from above, and the whole climb is inspired of walking the mountain. And it is actually quite a stunning view, and it's sitting there as a quite sort of low structure and giving you a little piece of Norway. And the more pragmatic side is that you can also fill this up and have an outdoor event in any time there's no sort of snow or ice. You can have thousands of people here, and you can have Justin Bieber had a concert. He would never be allowed in the inside of the opera. He came to the outside and created the wildest chaos in Oslo, having this sort of open to the public concert on this roof of the opera. This is the same sort of approach to the SFMOMA. The SFMOMA is, as you know, probably the SFMOMA even better than I do, but it's from 1985 in Mariobatto building, and it is a building that is quite a closed expression, even a beautiful closed expression. What I've been told is that the whole area at the time was quite, it wasn't such a good area, so they somehow created this closed expression also to sort of express that it is actually more like it looks like a little bit like a bank. And there's two challenges to the MoMA extension as the architectural, seen from the architectural point of view. And one thing is that they would like to double their program. This is about 198,000 square feet, and they would like to double. The other thing is they would like a new expression to this. The area is no longer any sort of difficult area to be in, and maybe they would like to change the expression to a more sort of public flow, dynamic sort of a city structure building. Well, this is not really representing that. And again, we have this sort of double way into it. It's the pragmatic direction, and then there's this poetic direction. From the pragmatic point of view, it was a lot about creating a site. Since if you look at the MoMA and the site and the city structure, they would like to double the program, but there is no site. So you sort of have to create a site. And there is no public flow through that area, so you need to create it. The way the approach went, yes, that this whole city structure has got this double grid situation. The main grid is the main entrance as it is today. It was the sort of main grid also for all transportation. But then there is this second grid. And the second grid originally was to handle the waste from the structure, which New York doesn't have. New York didn't have this second grid and had a lot of trouble with handling the waste as it grew and grew. This sort of secondary structure has become quite a popular public network, which is now then been part of the MoMA new public flow, in how we then created a secondary entrance from Howard Street, keeping the main entrance from the 3rd Street, and sort of weaving these two together, clearing out the site and creating a new public plaza at the end of Natoma Street back here. The way it's working is that this should still be the main entrance. This is the main access. This is where the MoMA should present itself. This secondary access is not secondary, but it's an additional access. It's actually then giving away a bit of the site for public free access, for a public plaza, and this is also a free public exhibition where you can go in and out of the building, and then MoMA can actually start opening up their gates and become more of the city life than a normal museum. And then we lifted up the meeting point in the main lobby to the second level up here. The more poetic direction to it, this first one was sort of cleaning up the site, creating a site, giving it enough space to double the program, is to both keep the main direction with the foreground of this sort of heavy MoMA as it is today, and the background of this telephone building, a really beautiful building, is to sort of slip in the new expansion in a middle ground, thinking about the middle ground as some sort of cloud between the cityscape and the landscape in the back. Mariobatto wasn't very happy about all this, but he accepted that approach, since his building is still the main focus and the main axis. So the whole exercise was to lift the program up and shift it to the side and work with the light to get these new public access in the public areas, give it enough daylight. That means that this facade towards the Howard Street entrance will be shaved out of the sun, and I can show you a little later how this facade will be the facade that we are working on continuously to make it the poetic side of the SFMOMA, while the other sides are more pragmatic to the city structure. So this is the middle ground, which is just behind. We're sort of chopping off the back end of the existing SFMOMA and sort of sliding in this new volume with another 250,000 square feet. This shows a section. If you see here, this main access through the existing SFMOMA, through the new extension, and then also through a parking garage in the back, where we've been allowed to have a public park, a sculpture park on top of it. Actually, all this sort of what used to be the back side has become levels of public and private exhibition spaces that all sort of terraces in the back, where you can, some of them are open to the public and some of them are part of the galleries. So we're lifting up the public to a second level where you can also look up into the sculpture garden and finally up to this roof sculpture park at the top. And this will be then the main foyer in the new complex. You can also then see the green vertical garden on the third level, which is part of the outdoor exhibition area. This is a rendering of the new Howard Street entrance, where you can also, this is open all the time. You can pass and go into the MoMA Street, and out in the other end, you can also then look up to the vertical garden. And this is the inside of the first sort of gallery that meets you at the entrance, and it's called the Howard Street Gallery, and it's a permanent exhibition with Richard Serra, and it's open to the public at all times. Another way of working with the SFMOMA on the sort of pragmatic side is to try and combine different program areas in one room. Like there was a large room that should be a multi-purpose gallery. They wanted an education area and a performance area, and they wanted an event space. And having no site, you will have to try and combine these. So this room, the white box, ended up combining all of these functions by creating a ceiling that could actually be lowered, and sort of elements that could be sort of taken out of the walls, and you can create this event space. And in some way you could say that to be this sort of compact in working with your square feet and square meters is also a very sustainable approach, and try and bring the city structure into where you can use all the space always and not leave sort of lots of square meters not used. Another big issue with the SFMOMA, there's a LEED gold certificate, and parts of that was working with the whole light situation. 80% of the energy use in these galleries are mostly the lighting. This is actually from the mock-up. This is the one-to-one mock-up they actually made at the SFMOMA, where they carried in all original art for I don't know how many $100 million and security guards to keep this mock-up going to test the light conditions. And what has been developed is a LED sort of background lighting that can always be on, using not much energy at all, and then you can support it with the spotlights for the specific art. And the whole thing is also an air extracts, and the mock-up in this room shows that it actually works where you can most of the time only use the sort of average light in the LED, and then occasionally use the spots, which actually quite a good concept to bringing the energy use radically down. Another part of the poetic approach is to find a way to work with light in the facade and how it can sort of reflect the San Francisco weather or climate in a good way. And as San Francisco is changing weather many, many times a day, to find a way to work with the facade where you can somehow play with this. This is the picture from the bay. This is an abstract from the picture of the bay. This is now a 3D modeling of an abstract of the picture of the bay, and this will then start the study where you can see the different changing light in this one facade to the new entrance will change with the changing light and the seasons. This is a one-to-one mock-up made by a local, I think his name is Crosby. It's a local firm that makes this lightweight reinforced concrete. It's a composite. It's really light, so that brought the steel structure down to a minimum. And these are, every panel can actually be individually just as it. You don't have to repeat anything anymore, because all of this is just 3D printed from this Crosby's machine and ready to be mounted. And this is how it will look in 2016 when they get all of this mounted. Then you need to take a deep breath. We're now going into the really pragmatic part of the lecture, where we are now outside of the Snøhetta approach. We are now going to our super team, and we've been met with engineers and people who are very focused on the energy use. Our codes are going that way. We can clearly see that we as architects, we need to know more than being poetic and pragmatic to actually manage to fulfill the task of making beautiful spaces, as long as we should count for energy use, for material use, for EPDs, for LCAs, for everything that needs to be documented. And we don't really know how to approach this, and it seems the engineers are better at counting than we are, so in a way we are sort of a little bit pushed back to the side. So this is part of the Snøhetta thinking we should actually be part of this movement. We would like to be there with the architect's voice and learn what will be our role and what should we think about, what is the most important thing to think about, trying to keep the emissions and the energy use down. We are in Powerhouse counting for energy. It's an equivalent to the CO2 emissions, but the whole approach to the Powerhouse is actually to be counting how much energy do you use and how little can you use. A main definition of the Powerhouse, because there's a lot of different definitions in sustainable architecture, passive housing, active housing, or at least we have a variety. So here is where we got the help from the university. This is how they will, at the Zero Emission Building, say that a building really is contributing and not sucking out of the system. If you can make a building that during its life cycle produce more renewable energy than it consumes for production of the building, the materials, the construction of the building, the operation of the building, and the demolition of the building, and the lifetime is 60 years. If you can have more energy produced than you can actually document that you used in 60 years, you will actually be positive. You will help the world and not suck out of it. And of course, to make it even a little more difficult, it should be built within commercial conditions. It should not just be a pilot project nobody else can copy. We would like this to be something that could go into the market and become methods and ways of thinking that everybody can use. Another thing that we need to learn more about is that the quality of energy should be at a certain level. There's a lot of architecture that you can create a lot of heat. You can have extra heat from heat pumps and other systems. But what should you do with it? You can make a swimming pool next to it, and you heat up the swimming pool. But not every project can have a swimming pool sitting next to it. Meaning that what we should aim for is maybe to produce electricity more than only thermal heat, which is making it a little more difficult. So the energy use that we produce should have a better quality, even or better quality than what we have been extracting out of the net. Passive house standard, you know that one? That you have a house that should be, airtight and run by itself. We are not counting for the appliance, the computers and the refrigerators and all that. This is operational energy that we're counting for. So in short, this should look like this. and now I'm introducing these little diagrams that will actually follow through the rest of the lecture, which might even help it a little bit to sort it all together. But the operational energy demand is what you use for ventilation and lighting and to running the building should be added together with the embodied energy, which is energy in materials, construction and demolition, which is a pretty difficult number to get hold of, but you should aim to get hold of that number. Like concrete is then a different number than wood, for instance. And when you add those together, you should be able to produce more renewable energy than this on site, meaning that you cannot just put up a windmill on your neighbor's site and take his chances out of making a positive building. You should solve it within your own site. This brings the super team together to be able to come up with such an efficiency and the productivity. All of these issues will have to be thought of at the same time. You need to have an energy efficient volume. You will need to have a super insulated building envelope. That's the passive house part. You will need demand control. You will need to work a lot with your ventilation strategies and find a way where it could use as little fans as possible. So natural forces will have to be part of your system. Daylight is really important since, again, in a commercial building, the lighting is the second biggest portion of the energy use after fans in the sort of the normal office buildings that are already built today. Heat exchange with the seawater or with the thermal geopumps. Then this, which is maybe the most difficult and most interesting part of the architectural discussion, is to keep track of your embodied energy in all the materials being used in the whole building materials, construction and demolition. And then, last but not least, the local energy production is nothing we normally bring into our teams at all in the beginning. Sometimes we've ended up having some solar panels, sort of, what should you say, mounted onto the facade after the building is already there and planned for. None of those numbers are even worth presenting when it comes to sustainability. It becomes some sort of a showcase for the solar panel industry, but it doesn't really do anything. If you want it to work, at least in Norway, we don't have that much sun, you need to optimize for the kind of use. You need those consultants in to the team from the very beginning. And what is our ambition? This is all very pragmatic, and it's all very engineer language. It's a lot of Excel sheets. I've never seen this many Excel sheets in my entire career. And the only thing that really makes people work at both Snøhetta and outside, where we get our engineers and clients, is to be ambitious and to be number one. And if you can tell the team that you should be number one, you can actually make them do anything. So this is how it all started. We just decided we would like to be number one to make an energy positive building in the coldest of Norway. And if you'd like to be number one, you need a team. Norway is famous for going to the South Pole and the North Pole. We like to be pioneering. And this is also something it's easy to get people inspired by. It's not easy to get inspired by saving energy. It doesn't work at all. Not on architects, at least. But to be in a team, a super team, that will be the first to the South Pole is really inspiring. And if you want to get to the South Pole, you need to be really efficient. You need to use your resources right. That's also easy to understand. You can't eat all your food in the first sort of 2 miles. You need to save some. And another very Norwegian thing, which is easy to sort of get us into, is to try and think that you should use the knowledge of technology to use as little technology as possible. Not just sit around and wait for the newest technology to just save us out of the problem, but use the technology that's already there. And we do really have more than enough technology to get this going in a positive way. But it's how you mount it all together, and when you start planning for mounting it all together, that seems to be the big difference. This is, by the way, a Norwegian invention, which we are quite proud of. So we made that a symbol for our work. Technology in our powerhouse should be this easy to understand. And here comes the challenge. That's the 40% of the energy use that seems to be belonging to the architects and the building industry. That 40% of the global energy use is somehow connected to buildings. Our comfort inside of the buildings, ventilation systems, all that, lighting. And the challenge is then just to get this, we need to get out of this. We need, as a group, not just architects, we need to get together and work ourselves out of it. So this is the super team, shortly presented. We are just one little hat here. This is an environmental foundation that's doing lobby work towards the politicians, making for instance, them listen to how our energy grids should be taken in energy from private industry and private housing, not only from waterfalls, make that some sort of a business. That's a bit hard for the architect to go out all the way to the politicians and do such work. So they're doing a splendid job on that. This is a developer. They're contributing with their sites. This is an entrepreneur. They're also quite big in the US. They are building, and they brought up a lot of competence in the energy field. This is a aluminum and facade developer, Norwegian based, quite big. This is us. And this is a consulting company who's got a lot of engineering going on in all fields of architecture and all fields of energy. This one here, without a hat, with the big glasses, are the detective. It's the professors that are watching our work closely. And I promise you, without this one here watching our work closely, we wouldn't have gone even a third of the way, since the ambitions and the sort of level of academia that are interested in this is such a big help to keep the ambition up. If this one says it's going too expensive, or it's too complicated to build, or we think it's too ugly or something, then this one will come in and say, hey, there's a bigger issue. It's not about you. It's about the whole globe. And we learned a lot from that kind of work, and we can see that if you're using this sort of interaction with the university as a what you call it, a catalyst or something, when you add something in chemistry that makes things happen in an odd way, and they are throwing their ideas onto all of us, so we can't just be the architect. We need to listen to everybody else as well. So we started. We found an appropriate building, which is part of the developers' buildings, which they would like to keep but refurbish. It doesn't really matter where it is. These buildings are everywhere. It's quite a generic problem that they are built in the 80s. They use, this is the square feet issue, but about 220 kilowatt hours per square meter, and that it will be then, Erin, all this is divided by, that would be like 22. And the facades are outdated. They're 30 years old. There's nothing wrong with the structure. There's nothing wrong with the building. So maybe one of the main approach in the pragmatic side is if you can use it, you should use it. If you'd like to lower the CO2 emissions like right now, you shouldn't build new things before you really checked out if you can use what you got. Not all my colleagues really appreciate this approach. But I think we will have to learn that will be part of our work, to be creative within the frames of what is already there. So what we did is just picture that we stripped this thing down for the facades, and we sort of brought in all the issues for the diagrams later on. And they are not in a sequence of priority. All of these issues go in parallel in all discussions from the first sketch. First of all is the reuse. If you have something you can reuse, do reuse it. The structure and all the concrete and steel could be remain. That helps the embodied energy to come down. And then recycle. This is all basics, but still it's about having this as part of your design parameters, which is maybe not as basic. Heat recovery means that you will reuse your heat from the ventilation system. Seen from the architectural point of view, the ventilation system can be whatever it like in a way, but the materials that you that you sort of put into your room and the dimensions of the room has got a lot more to do with the energy use than we maybe thought. So to be part of this discussion with the engineers on the ventilation strategy as you design it has been probably how we can bring it down. The same with the comfort criteria, to discuss that maybe some materials are doing more for the air quality, that you choose materials that don't have any emissions into the room, that are making the acoustics work, so the acoustics doesn't again ruin for the ventilation strategy. All of these discussions on materials has maybe been the most important part of all, and it's also universal to all the fields of engineering and architecture. It will change eventually. Try again. Energy supply system. In this case, we're using energy wells. And again, you can think that that doesn't really have to do with the architecture. On the other hand, we need to know where these areas for the energy wells should be and how they're connected to the ventilation strategy and how they're connected to all other supporting systems, which is again pointing back to the materials and the area efficiency. It also helps us with the free cooling, that we can, if you think correctly, you can go with all the excess warm air into the energy wells. And I suppose this is quite a normal system in the US as well now, that you use the thermal systems to sort of help off the energy use. In a way, I think I used a little time to understand the difference between the thermal energy and the renewable produced energy, since how we've been thinking here is the geowells and the thermal energy is actually just helping us bringing the demand for operational energy down. We don't count for the sort of heat that we can bring up of the geowells or the cooling as renewable energy. We just use it as not doing anything with the electricity for the as little electricity as possible into your operational systems. Does that make any sense? Because it took me about half a year to clear out the difference between the thermal use and the electrical use. I never really cared too much what was in my heaters, but now I do care about that. The other thing with the energy supply system is the solar collectors. They can bring in the hot water for the tap water, for the showers, maybe more important in the housing areas or housing than it is for commercial buildings, but still it is doing 40% of the total energy use you normally have for heating up water you can do by solar collectors in Norway. And I suppose that will be a worst case. What we actually found out in the end was that the server room, the excess heat from the server room did the same thing. So we could choose whether we wanted to use solar cells or the excess heat from the server room, which is also quite interesting. And another energy supply system is district heating. So all of these needs to be worked together in this sort of paperclip way, where you know that if you listen to just every producer of one product after the other, they will always claim that it's this and this efficient and it will help you this and this much. But when you put them together, they don't really work. So you need consultants from the very beginning to make these, just take away the things you don't need and the things you go for, make them work optimized. And as you can see, all these weathers are in Norway at the same time. So you've got the summer and the spring and the winter going on for one day. So these systems will change on and off. Yeah. Probably it's just pointing. Yeah. And then this is the last tricky one, is the climate envelope. We've been sitting around for maybe 5 years just waiting for the insulation thickness to go down by itself. All these, aerogel thing and vacuum panels, but it's not just happening. It's too expensive, and they can't always, if you go for the embodied energy within some of these materials, they're not really worth it. So we did end up with a quite thick wall. It's about 40 centimeters. It's a little more than a feet thick, which is it's okay all the way to you come to your daylight issues. which we now have to learn to measure from the very beginning as well, since the first two sketches for facades really didn't have enough daylight at all due to the thickness of the wall. So it's just bringing in another dimensions of studying. This is a very general plan. It's got a 30% cell offices and a 70% open landscape, where we have a sort of core and extra is meeting rooms and staircases and all support rooms in a sort of a core. It's not only core functions, but it's sort of enveloped in a shape. This is then going through what we actually did. The first one was more in general. This is how we thought about the reuse. Of course, we looked, the concrete is there, the steel is there, but the facade, I mean, it's dead as a facade, as a climate envelope, but all is glazing. We actually reused in our meeting room structure, because that doesn't require anything. You can take the glass and you can ask the builder to incorporate them in new frames and put them up, and then suddenly you can, in your embodied energy budget, you can just rule out all the meeting room glass walls, which is actually quite a large sort of budget of energy, not really used for anything good. So that worked out. Another interesting thing with the energy supply system would be that when you think about the embodied energy for these concrete technical spaces that end up under the surface of under the surface, they will have to be waterproof, like a bathtub. That means a certain concrete, there's a lot of carbon, and when you start pulling these numbers into your discussion, and you know that you need to have even more solar panels on the roof, the more concrete you add in, the more solar panels you need, then that's an expense. Then suddenly the team of engineers seems more and more interested in keeping the technical spaces on the top in the existing structure and maybe really small. We always had ventilation engineers pumping up the largest rooms. They don't have how much equipment they want, but they always want like the whole basement to themselves. But that discussion sort of just went away when we started counting for the concrete, which is actually quite an interesting part of the development of the whole room program. And they ended up on the roof, not on the roof, on the top floor, really compact. Another thing is to use the existing shafts, the stairwells and the shafts for exhaust and the whole extract system of the ventilation air. Since the air is really slowly moving, it's like a really low-speed ventilation strategy, the air will be fitting well into your stairwell as you are climbing the stair. You wouldn't even notice. That takes out all the shaft area, which is making the whole plan more efficient. We added an extra stairwell as well for a vertical sort of communication and the visual look from floor to floor. And even that one worked fine as just extracting the air without having any walls. Again, that means that you can take out embodied energy for a lot of just channels of metal that takes the air, to transport the air. And that was also then challenging for the ventilation engineers to take as much of these out and keep the distances as short as possible. We have a ventilation engineer who usually demonstrates this by showing that if you have slow air, it's like you're walking slowly in the room, not using any energy. But if you start speeding up and running around in the auditorium, which I'm not going to demonstrate, you will use more energy. So if you can have air just come out slowly on the floor level, it will actually walk itself where people are, because you have a higher temperature. So the air will actually transport itself to where it finds people. And when you're done using the oxygen in it, it will just leave you and go away up in the top, like just disappear in the top of the ceiling. That means that your transport distances, but actually the air will do it themselves. It's a quite clever principle called a hybrid ventilation system. And that brought our fan use down to 1/10 of what it usually is. And we use the same system for heating. Actually, we don't really need heating, because the whole climate envelope thing is so airtight, that there will probably be no need for heating at all. As for extra cold days, there is a ventilation strategy that takes care of the heat. And here comes the part that really was worked well with, and that's the acoustics. The ventilation engineers and the acousticians are constantly disagreeing, and also with the architect as well, about how much of these absorbents you should actually put in your ceiling. They are made out of materials you don't really want to account for. A lot of them are really bad stuff. They are lowering the ceiling height, which the architect doesn't like, and the acoustician seems to really be safe by doing both carpet and absorbent in the ceiling. And then the ventilation strategy comes in and saying, if I should make my super elegant self-walking air to work, I will need at least 40% of the ceiling to be thermal mass, or else it won't work. So then the acoustician will have to accept that 40% of the ceiling should be concrete. Freaking out, thinking that we need to compensate, and all of these walls, which he really didn't like in the beginning, now became part of the concept of the acoustician. We took this for his own, and it became actually quite an important part of the design. And we made even a prototype, which is now for sale. It's just wool in strips. The whole ceiling and this wall concept became then part of both the ventilation strategy and the acoustician strategy, which is quite some sort of a building integrated system. So the acoustic ceiling will then be lamellas, that's taking the daylight into the room, and within these lamellas there will be 40% concrete for the ventilation air to cool down. That also brought the embodied energy radically down, that we could skip the carpet and skip most of our ceiling absorbents. Again, to have all these engineers in the same room as you when you are designing this is the clue. To bring this acoustician in the last part of the project, which usually happens, we will have absorbents everywhere. That will be the only way out of it. So this becomes the ceiling plan with the diagonal strips. The light will fit in between. And this will become the envelope. And the envelope was also going through a discussion of embodied energy. The existing envelope was maintenance-free for 30 years. It was glazing and aluminum and a very high embodied energy number. And part of what we learned is that when you should use glazing, you should use it where you need to see out. To sort of put the whole sandwich facade with all that glazing gives you a really heavy budget for embodied energy, which again needs to be produced with more renewable energy, which we didn't have any more roof space for that. So how to find a maintenance-free office building facade without using steel and glass and aluminum was to find a Japanese technique of burned wood. If you burn the wood in a certain way, and hopefully not with the gas, we sort of made a sort of what's it called, wood coal mock-up, where you can burn off the wood in such a way that no bacteria will actually live on the surface, which means that it won't rot, nothing will happen to it for about 100 years, at least in Japan. Let's see how it works in Norway. But we got the entrepreneur to do this and made the whole, and now it's actually mounted. This building is actually ready in about 2 months' time. And that brought the embodied energy down radically. And the whole discussion with the facade certainly become an interdisciplinary discussion as well, which also is very interesting. It's more than just being insulated. So then we have made a passive house building out of this with a burned wood, with 40% transparent facade and 60% opaque wall. We managed to keep the U values right. We have a sunscreen system which is integrated. We can open the windows. The air is so sort of slow moving that there's no problem with pressure when you open the windows, which I think is really good, that the windows can be opened for extra air whenever the user wants it. And then we have the PV modules on the roof, but we have a limited roof area, so there's also part of the discussion was, okay, if you do this and that, then you will blow the budget for roof area. So it all, yeah, there's all these Excel sheets that sort of popped up explaining how much we could do of different impacts. When we move into the building, you will then see an interior that doesn't at all look like it did before. We will have this staircase as part of the ventilation strategy. It only has a glass railing of about 1 meter, and that just lifts the air from floor to floor. We will have these lamellas of absorbent wool, lamellas, and the 40% of concrete in between, and then the light fits in between there. And all of this wall is both making different zones and areas where you can keep the quiet areas out of the noisy areas, where you can have people walk, where people don't work, and also have it be part of the ventilation. Air is coming out along the floor, and the air is sucked back in at the top of these walls. And the final part, when we've done all these reductions and we made this work as efficient as possible, then, of course, still wintertime in Norway, we have a power consumption. It's low, but we still need energy. So that's sucked out of the grid. But then we have quite a long spring, and we have quite also a mild autumn in Oslo. So the power production on the roof will then be larger than we can actually consume, meaning that we can feed back to the grid and planning for helping the transport sector to get low carbon as well. In a way, you could say that if you can manage to produce energy on the buildings that exist or in new buildings that you are planning to build, you can use the infrastructure which is already there, which is a very good thing. And there is no chance that the transport sector will ever have enough. So the discussion on whether it will be an overproduction or not doesn't really count, at least not in the city. So far, our the companies are positive to this. So it seems that it will work. And the last picture from this project shows something which hopefully looks exactly like this in about 2 months' time. And it should be an environment that is a very sort of daylight environment. That's maybe the main issue, I think, seen from the architect's point of view, is the material and the daylight issues that seems to be our part of the work to keep our eyes on and to sort of make the rooms stay open, airy, and beautiful. Then there is this last project, which is it's still a powerhouse. It's the same methodology, it's the same team, it's the same people. Well, this is how this project now is shaping itself. It's not an existing building. This is how these parameters are shaping our architecture in a way we have not tried before. We made a statement quite early in that project that was form follows environment, which in this case was quite right. It's in Trondheim. That's where I'm from. It is there. It's quite far up. It's 63 degrees north latitude. It's got a mean outdoor temperature of 5.1 degrees. It is a radiation of 101. I'm not really comparing it to this area. I'm not really sure, but I'm telling you, this is not much. This is, say, an area where you could think if we can make it here, we can make it anywhere. It really is not much sun. I grew up there. I've never had any thoughts about it having enough sun to run anything. And even the solar power industry was quite impressed by the fact that there was more daylight and sun up there than they thought. We don't do any measurements on irradiation in Norway above this point, thinking the rest doesn't have sun, which is a failure. There is a lot of energy going on all the way up to the north of Norway. So this is our interpretation of the sun. We do lots of projects in the Saudi Arabia and the regions around there, and the map and the color of the map is giving an impression of sun. And they just lay out these solar plants everywhere, and they're doing fine. But this doesn't look like, this is blue, and this is red. But looking at it more closely, you don't have to go that far. You can just go to your cell phone and measure that this is Riyadh, and this is Trondheim, and this is the sun, and this is the sun. Because the only thing is that there is actually quite an even amount of sun even in Norway, but the angles that the sun hits us is really unfortunate coming to harvesting. So if you would like to harvest the sun that far up north, you just need to take into account what kind of angles you can actually use. You cannot make a horizontal solar plant that you can in Riyadh. Another thing which is quite different is that in Riyadh, for instance, you have a very predictable weather. In Trondheim, you don't. This is the weather diagram in an abstract level for Trondheim. There is so many different climate data to keep track of. And to be honest, we have never paid enough attention as architects to this kind of data to really make local architecture work, which we have changed now. And again, new processes of this super team are bringing all of these people, all the different knowledge with the sun and the climate and the weather data all together. Okay, this way. And just to give it a really basic short story on how it worked. We're working with this Autodesk Acoustics program, which is maybe the program we got right now that can measure the most of the sun and the wind. We know that we need to make an efficient volume, not to lose energy. We know that we need to utilize the solar power really efficiently. On this site in Trondheim, 30 degrees to the south will be the optimal over the year. It's a little steep, so to get it through in the municipality, we'll have to lower it to 20. We lost a lot, and we needed to come down on the square meters to be able to compensate for that. We also work with the wind, and I promise you, if you've been to this site and known Trondheim, you would think that will do it. It's just very, very windy. But to work with windmills in architecture efficiently, we realized had not really come far enough. To be able to make a powerhouse out of this site, we would need 13 windmills that had to be 10 meters above the highest point of the building, rotating all year. And with vibrating parts in the structure, we needed to add so much concrete and steel to make it stable and safe that it actually just zeroed out on the whole energy production. So we just need to remove that idea. But still, the studies on the wind pressure was very good for the ventilation strategy. So that is absolutely part of the studies used to do. But so far, we have not been able to make it work as a sort of power production. What we did use was the solar power and how we actually, as architects, then need to look at different models and how you can optimize for the sun. This was the first sketch. The yellow part was the only one doing a really good job. The blue part didn't do anything. So to make this work, we really needed to go for the full optimization of solar power harvesting for the site. Looking at the footprint, where is the south direction? What is the degree you need to sort of tilt your building to make it work? Optimizing the usable volume after you're doing these studies. And this is how it is going to look. Also optimizing for daylight in the center. This is a 2,200 square meter. Yeah. That will be another 0 to that in the square feet of building integrated photovoltaics. That will actually serve this whole building. There's also a bit of the facade that will be the same panels for the west and a little bit for the east and also some for the south. There's challenges with this solar panel work of the architecture is they don't really come from an industry where they are used to our measurements. They come from solar plant industry. They talk in this language, kilowatt peak, and they talk in dollars, and they don't really relate to any of our sort of building industry language. They would like things to be, do you want them in purple, or do you want them in silver glazing star, or what do you want? And as architects, there's part of the discussion is to try and get this industry to find a sort of communication on what you would like it to be looking like, not just for decoration, but for a roof panel. So what we wanted was a sort of slick black surface, no dots and no wires. We just want it to look like a normal roof, so we can take out the ordinary roof and just use this one as the roof. That's making the embodied energy lower, and it's also making the price sort of doable. And it should be maintenance free. The snow should somehow slid off it without falling into somebody's head. There is a lot of answers out there which the industry of solar power has not really come back on. So we are now going for a mock-up to see how this actually looks and how we can maintain it out of snow. The snow issue is not really that bad because parts of the year where there's snow on the panels, there are no sun to harvest. So it could be snow, it's fine. And as soon as the sun comes back and is doing a little job, then it will sort of slip off. So the problem is how you can make it slip off without slipping into people's heads. And these are the diagrams that we work with to optimize the different surfaces. You can see that even for the north facade, there is actually possible in an open situation to harvest solar energy. And part of what we realized was that this cold climate and really windy climate are making the panels a lot more efficient than the solar plants in Riyadh. So the cool ventilation is actually bringing the efficiency up quite a lot. But if you start counting for embodied energy, for silicium and these solar panels, there is a sort of breaking point where it's not really worth it. So you should use them correctly and optimize the energy production to really, I'll show you a diagram where you can see the embodied energy for different elements, and it's not really the best thing. This is the facade, which is actually quite a lot a rational approach to how the solar panels are being used, where you have a surface that can harvest. There will be more opaque panels. Where there's this north facade, where there's not much sun to harvest, you can have a more transparent facade, which is also quite the same as the daylight study will show, that where there's a very open and sunny situation, you will like more closed facade. Where there's a first floor area, not much sun to harvest, you would like to have an open facade. And still we have to be within this sort of 40% of open to and 60% opaque to keep the passive house standard. And then this will be a daylight optimization of this atrium space. And this is actually self-shading, so you hopefully don't have to have the solar shades down all the time, because the building itself is creating the shade you need in the office space. These are all numbers that are related to the square meters. But I don't know the numbers for average energy use in your buildings, but this is at least quite low for our standards. If you measure this up, we brought the whole delivered energy for operation of this office building down to around 2.9 kilowatt hours per square feet per year. And the largest thing which is left for us to work with is still the lighting. And this is LED. And this is, you're not using the light if people's not in the room. All of that is still handled, but of course it is still more daylight studies to be done for architects to bring this down. The fans are now doing fine. The ventilation heating is quite low. Here you go for the embodied energy. Concrete, steel, photovoltaic. So it is part of the discussion is when this kind of sustainable approach is correct and when other kinds of sustainable approach is more correct, because there is quite an impact to using these. But of course, over 60 years, they will pay themselves back and even contribute. But if you're mounting them on the north facade, not creating any energy, it is maybe not a good sustainable way. In a city situation with a lot of shadow, for instance, if there's shadow of one panel, all 20 panels will go down on production. This is also part of the issues we need to come to terms with. So not to be skeptical, but it's about knowing, not guessing, and asking questions and using people that know. This whole study was done by the university. I don't have a clue how we could have done it without the university, because we don't really have the knowledge. nor the archives, or really knowing where to go to find information. But we are now building slowly up an archive and an understanding of how we should keep track of our materials as we make decisions, and it certainly changes our decisions. This is the energy production, and then if I go 2 back, that wasn't that easy. If this is then the energy demand, you add that together with the embodied energy. You can see those two are quite similar in size. If you are making a really efficient building, you will probably then see that your material budget is a lot more visible, while if you have a really inefficient building, materials are nothing. These two are about the same size for a new building. For the first example I showed you, it's about half, since we used the concrete and the steel again. And we also managed to reuse quite a lot of the glazing from the outside. We actually brought the embodied energy down a lot, down to 15. It meant less solar power on the roof. Well, this is a good example of the most efficient new building. And then you need to have enough roof, enough facade to compensate for the first two. And then we really made it just about with a 5, which would be a 0.4 extra over the 60 years. So it's not like a power station. It's just about to contribute and not just consume. And as you can say, it still makes a really difference to how you think on commercial buildings. If this is a number for a average building where we came from, this is the first example of the black 1980 building. And then this is our code at the moment. It's about to change radically just right now. This is if you go for a code building but with improved ventilation strategy, where you have this slow-moving air and a lot of natural forces. And this is where you go for all of that and the passive house standard, and you heat your water. And this is us. We are actually producing all of this yellow energy, and we are then compensating for both. The reason this is a little confusing, none of these are actually counting for materials. Nobody are actually counting for materials. This is the only buildings that we know of that so far, I hope you probably know it, is counting for materials. If you would like to do a lifespan analysis, that's what you need to do. Then this is the materials. This is the operational energy. So you need to give back both of those. And that gives a completely new architecture. And we were all quite surprised when the model showed up looking like this, thinking that was quite a strange office building. On the other hand, we quite liked that it was looking very different, since it's created in a very different way. We've thought in a very different way. We've worked in a very different way with a lot more consultants. And we were up in a team of 25. And hopefully it will also be a point like the opera where people can go and actually see and experience something of sustainable architecture that will make an impact both in the city and in the technology, and the university would like to come there and use it as a sort of display. That was it. Wake-up call.
Go all the way to the light. So we do have a few minutes for questions if we have. While you guys are thinking, maybe I could ask one. I'm interested, obviously, in this kind of per-year embodied energy versus the per-year operations energy, but also seeing it in the context of the 60-year life of the building. And was wondering if in any of the discussions with your team, there's been talk about the timing of those emissions or energy use, thinking that probably the embodied energy use is weighted towards the kind of construction years and maybe has a different climate impact in the near term than in the long term?
Of course. So since the global problem is right now, we should actually stop building. It's a really bad advice for the Department of Architecture. But yes, that's right. So this 60-year is actually pushing the problem a little sort of in front of us, while to use the existing structures in a very creative way is keeping it down, because then you will skip both the production of the materials and the transport of the materials, and you will have a demolition process, which is you have to take down what's not working and recycle it. But still, it brings it down radically, and in a way, if you should think this way, it's a lot easier to make a powerhouse out of an existing structure. And this first building, this sort of ordinary office building, it's become a very popular topic for politicians to bring forward, since it's not about architecture only. It's more about a strategy politically as well. It's a lot more people that could sort of add on to the discussion, since it's not about a Snøhetta project or, being very sophisticated about design and all of that. It's a more sort of pragmatic approach, and you could easily add up that you can bring down your CO2 levels radically if you can make these structures as efficient as new structures. Then that argument of building new structures because it's more, you can pay back within 15 years something, that's now dead. We're done with that. You can do the same efficiency in most existing structures, but that needs a different knowledge and maybe to bring this material thing in. If you count for materials, it's obvious. If you don't count for materials, it's not that obvious.
I very much enjoyed the way you added the staircase in the renovated building, and I'm wondering what impact did that staircase and the ventilating shaft have on your fire suppression system?
The fire?
The suppression, fire suppression sprinkler system?
It didn't have really any impact. The fire engineering was done simultaneously, of course. We needed a curtain that comes down in case of smoke. Apart from that, the extract is done in the same shafts as the ventilation with the, what's it called, I don't know a word in English, what you put in your shaft when you need to stop. Damper, that's it. But the strategy for fires is all in sync with the ventilation strategy, and that staircase is not part of the escape route. So you can just in the case of fire, you can close it off so that smoke doesn't go from one department to the other, but no people need to run down.
You didn't talk about peak loads.
Loads?
Peak loads.
Peak loads. Peak loads are handled by the district heating in the one project. And actually the whole discussion of peak loads are actually toned down by the whole passive house envelope is reducing these peak loads radically with the U values of these windows and this whole envelope. The climate inside of this building is quite easy to control. So hopefully we don't really have any use of it, at least not in the Oslo region. But that might be different from site to site, of course. I don't know if district heating is something that works here, where you have, that's like the city's waste is contributing to hot water that comes into, you're having to use it if it's there, even though some of that waste is not always the best system sustainable-wise. But
We actually removed it from our downtown.
You did? There's a question back there.
I'm curious how you deal with 40 years or 60 years. You have to be engaged in this project for 40 to 60 years, because in our country we find the money to build them but we don't find the money to maintain it. And as the systems wear, they don't get replaced. Or the building changes use. And architect B, or building engineer B, changes everything around because they're working on only the prescriptive uses and not the energy uses. So I know in light fixtures there's an energy efficient quotient, but I'm wondering how you deal in Norway. Are people that committed that they'll maintain these buildings, or do you have to sign on for the rest of your life to oversee the maintenance of the building?
I've signed on for the rest of my career at least to follow this up. Well, this is an obvious problem or challenge, that the user will have the greatest impact on how this actually will go for a plus energy result or not. The good thing about these two projects is that the developer they are owners of the buildings and they will rent them out, and they have the same ambition as us to keep measuring. And it's also since it's got the status of a national research project in this SEB program, they will be paid a lot of attention to the measurements. The good thing is that most of the clients that will rent will want the Powerhouse or the plus energy sort of stamp for their own green advertisement. So there is something in it also for the user. If they can make it work to a positive result, they can also use that as a showcase for their own business. Since there is not many buildings who have done this previously, I think hopefully they will put some pride into making it run in this way. But of course, in a way, these building integrated solutions have got an upside, since the architecture are supporting the technical systems. It seems easier to make them run. If you made the material choices and you kept the ceiling in concrete, it's less sort of fan power, it's less technical systems running. On the other hand, if you start tearing everything down, changing the ceiling, then suddenly everything is gone. Will you?
Maybe your question, Kelly, maybe could be the last question after his. So go ahead.
I'm really interested in the interdisciplinary collaboration aspect of the work, and I was wondering if you feel like we're moving towards a future where these people from different expertise will be kind of working in the same firm, or if there's an advantage to having sort of one guy from engineering and having like multiple different firms coming together for a single project.
I think it's a good thing to be separate teams. That means that we can have these workshops where we can all get together and come with different opinions from different angles, and have these scientists that really mix everything up for us, and that they have some time in between every workshop to be architects, for them to be ventilation engineers, and for the acoustician to do acoustician work. And I think we found that was a good model. So when all of these parameters are thrown upon us as to become design parameters, so that we can sort of be at home for a few weeks and also get back into developing beautiful spaces and good environment for people to be in inside and outside, was necessary. And then throw yourself back into the interdisciplinary work. I think you might risk, if you are sitting in this Excel sheet world all the time, that you will lose your, what should you say, you will become less brave as an architect, and you might end up with being very sort of safe and secure, making shoebox models where everything can be measured at any time. And we have this kind of separate development going on actually in the universities, not in the architectural department, in other departments, where they think that buildings could just be shoeboxes, because then you can control all the surfaces and the windows and the heights and everything, and then it's easier. While we come with things that are on an angle or in a shape, it's a lot difficult for these measurement programs to really cope with it. So I think that's a really risky way to go, that you just compromise and make things simpler just because an Excel sheet is being added onto you. I think we just need, as architects, to be able to count and document. You just probably have to get used to that and not give that part of the work away. Should I say something about the rhino and the grasshopper thing as well? There was one more question.
Yeah, actually going off of this question, who initiated this collaboration between these various organizations? Was that like a national thing? Was that an architect thing? Was that a university thing?
If you remember the sort of super team helmet people, is the one to the left, the Environmental Foundation. They have a big national conference once a year for everything sustainable, all businesses, not only building business. And they felt that the building business was so much lagging behind that they just threw this challenge into this big auditorium saying, what's wrong with you? Why are you not doing anything together? And then the Norwegian hydro company, they were the first to say, okay, we'll fix it. And then they managed for a few months to gather the team. And all of the participants were already part of the SEB program, also the Zero Emission Building program at the university, which is the biggest Norwegian sort of research program for the building industry. And it's just become some sort of a championship. That's how it worked, really, to be the first to go for the positive energy collaboration in Norway.
So the sort of payoff, as it were, for all of these companies is, again, that competition aspect?
It was a sort of self-made, it's not really a competition, it's more, we can do it, sort of a thing.
But I mean, if this model of collaboration is to be replicable, say, here in the States or in other countries across the world, what is the incentive? Thank you. What is the incentive for this, for all of these companies to make sacrifices with the other companies and to have that collaboration? Is it just a moral thing, or is it?
Well, if you would like to go that far in sort of energy and emission, you will have to collaborate that way. And I think everybody who tries to do this sort of solitude will not succeed. So in a way, it's more showing that it's actually how it can work. Hopefully, we don't need 25 people in the team in a few years' time. We've hopefully, as architects, we've learned to handle the material part, so we can sort of skip a few people there. We will probably do the daylight analysis ourselves, so we can skip a few people there, and we can do the measurements of heat loss and U values. We should really do that. I mean, we had 3 people on that case. What a mess. And we can also probably get a little more independent in doing these energy production studies. The software they're using, the PV system, is really banal. It's very easy. You can add in the product, the angle, the latitude, and there you go. It's not really that hard. But to make a whole system and make it work and, count for what it should cost and everything, that's of course more competence. But as an initial phase, I think, not to say the architect can do everything, but to just get used to that there will be more parameters in the future. Up until now, we had landscape urbanism, interior design, colors, light. We have quite a lot already, but now there will be some add-ons, and there shouldn't be other disciplinary people. It should be us having a little broader perspective, and then maybe invite people into our teams a little more often, and realize that our designs are not that superb, that they can be just second-handed, given away to the ventilation engineer 2 months down the road, because then he or she will probably be very dissatisfied with the result. So I think actually the architects could take that sort of little open-minded role and get more knowledge. And yeah. But I don't know if that really answers your question, but I don't think you really need more initiative than wanting it. If you want it, whether the code requires it, or you just want a gold medal or a platinum, whatever. If you want that, then you need to work this way.
Are you willing to take one? Okay, that's fine.
Well, at least last term, Professor Murray was saying that in the United States we don't really do that. It's more something like European countries are the ones that are more advanced in this kind of collaboration and making our buildings, more heading more towards, essentially the powerhouse. So I'm just wondering, how did it get to the point where, or how can we in the United States get to the point where we're behaving kind of like Europe in that sense, where we're like really just because we're being moral or something, we're actually doing it? Because I know that like we as students, we want to do this because it's, we're optimistic and such, but it doesn't really seem to happen in the United States. And I don't know how we could possibly get to that point where we just do it because we're collaborating. You know what I mean?
Yeah. I think moral doesn't really work. Not in Norway either. No. This number 1 slide that I came up with was actually what's worked. It's just the sort of competitive, eager to be number 1 or first or highest or best or deepest or whatever. But since it's quite obvious that the world's got some challenges and it's quite obvious that we got part of the responsibility, it's not really all that moral it takes to make people want to participate, as long as you don't talk about moral, but talk about, getting your act together and doing things better. I think now the building industry in Norway is a lot further ahead than the code. And maybe also that's right, that the code is like a minimum. Some people are still very proud when they reach the code. But sort of, we made code, if you got quite a strict code, but it's not that strict. But to be sort of thinking that code or rules and regulations should be pushing us in any direction is probably not working. So we should have the initiative to go as far as we can with the knowledge we have. And I'm really quite optimistic that the industry will do this by themselves in a way. There's so many competitive people in the building industry that this should actually go by itself as soon as you could prove it's buildable within a normal economy. If this was a double price building, it would never work. But since it's within budget and the budget is within reason, why shouldn't the next builder do the same things? And all of the materials are on the shelf. It's nothing sort of radically different with this than the others. It's just more consultant work in the early phase, but less consultant work in the last phases. We don't have to compromise on every single detail in the end. Less arguing with people is also part of the good environment.
Can we make this the last question then?
Along those lines, and I'm assuming that as these Powerhouse projects go online, there's going to be monitoring of their success rates. How much transparency of that is there going to be? Are these things going to be published and available?
Yeah, 150% transparency through this university in Trondheim. You can log on any time and see how it's going, and there's thumbs up and thumbs down from different professors and different. That's available. Yes, this is the good thing, that it's not a sort of trademark thing or a branding thing. This is absolutely meant to be helping the industry, whoever is interested, to take the results and just rip off the recipe of how to make a powerhouse out of a renovated building. Be my guest. It's.
And you said it's through the website of the university?
Yes, it's the Zero Emission Building, and it's all in English.
Thank you.
In a very scientific English, hardly. Maybe for need some special interest to get a little far into it.
Thank you very much.
Did you get any wiser?
Yeah. Certainly.